Hello there, and welcome to this quiet corner where curiosity meets the vastness of time. Tonight, we are going to explore something gentle yet profound, something that might change how you think about our planet and our place on it. We are not going to rush through dramatic theories or shocking revelations. Instead, we will move slowly and thoughtfully through one of the most fascinating questions science has ever asked. What if we are not the first civilization on Earth? I know that might sound like the beginning of a science fiction story, but this is actually a serious scientific question, one that researchers have been quietly exploring in geology labs and research centers around the world. It is not about finding ancient spaceships or mythical lost continents. It is something much more subtle and much more interesting. Before we begin this journey together, I would love to know where you are listening from tonight. What time is it where you are? Are you settling in for sleep or perhaps taking a quiet moment during your day? Wherever you are and whenever this is, I am glad you are here with me. If you find this kind of gentle exploration interesting, I would be grateful if you could share this with someone who might enjoy it too. These quiet conversations about science and wonder work best when they can reach other curious minds. But there is no pressure at all, just an invitation to think together about the deep mysteries that surround us. So settle in if you can. Maybe lie back and let your thoughts slow down to the pace of geological time itself. We are going to take a long, gentle look backward through time, not just human time, but the vast stretches of Earth time that came before us. When we talk about ancient history, we usually think about a few thousand years, the builders of the pyramids, the people who created Stonehenge, the first cities, and the earliest writing systems. Even when we reach back to the very beginning of human civilization, we are only looking at about 10 or 12,000 years. That feels like a very long time to us. It is enough to fill countless books and museums and university courses. But here is something remarkable to consider. Those 12,000 years of human civilization represent just a tiny fraction of Earth's story. If Earth's entire history was a book of 1,000 pages, human civilization would appear only in the last few words of the final sentence. Earth is old, very old. Scientists believe our planet formed about 4.5 billion years ago. That is 4,500 million years. For most of that enormous span of time, there were no humans at all. For most of it, there were not even mammals or dinosaurs or complex life of any kind. Let me help you imagine this vast scale of time. If you could travel back 1 year for every step you took, you would need to walk about 25,000 kilometers just to reach the beginning of human agriculture. That is more than halfway around the entire planet. But to reach the beginning of Earth itself, you would need to take 4.5 billion steps. You would circle our planet more than 100,000 times. This is what scientists call deep time, time so vast that it challenges our ability to truly comprehend it. During this enormous stretch of history, life on Earth changed and evolved and experimented with countless different forms. Most of these experiments and living have left no trace at all. They came and went in the great dance of evolution, leaving behind only the faintest hints of their existence. So when we ask whether we might not be the first civilization on Earth, we are asking about this deep time. We are wondering whether somewhere in those billions of years, some other form of life might have developed what we could call civilization. But what exactly do we mean by civilization? This is not as simple a question as it might seem. When most people think of civilization, they think of cities and writing In complex technology, they think of things like the ancient Greeks or the Roman Empire or modern industrial societies. But perhaps civilization could be defined more broadly. Perhaps it is really about any form of life that develops complex social organization, life that can share knowledge across generations, life that can modify its environment in sophisticated ways, life that can work together to solve problems and create things that would be impossible for individuals working alone. If we think about civilization this way, then we might ask whether other species on Earth today have civilizations of their own. Social insects like ants and bees certainly have complex societies. They work together in sophisticated ways. They build structures and solve problems cooperatively. Some scientists would say these are forms of civilization, even though they are very different from human civilization. Dolphins and whales have complex social structures and communication systems. They pass knowledge from generation to generation. They have cultural differences between different groups. Could this be a form of civilization too? The more we learn about other forms of life on Earth, the more we discover that intelligence and social complexity are not unique to humans. They have evolved many times in many different ways, and if intelligence and social complexity can evolve today, they could certainly have evolved in the past as well. This brings us to our central question: the vast span of deep time before humans appeared. Could some other form of life have developed its own civilization? Could there have been intelligent social creatures with complex technologies and knowledge systems that we know nothing about? This is not just idle speculation. It is a question that scientists take seriously. In fact, there is even a name for the scientific investigation of this possibility. It is called the Silurian Hypothesis, named after an episode of Doctor Who, but based on serious scientific thinking. The challenge is this: even if ancient civilizations did exist, millions or hundreds of millions of years ago, would we be able to detect them today? Earth is constantly changing and recycling itself. Mountains rise and erode away. Ocean floors spread and disappear. Continents drift and collide. Most of the evidence of anything that happened millions of years ago has been erased by these natural processes. Think about our own civilization. We feel very permanent and significant. Our cities and roads and monuments seem like they will last forever. But geologists who study deep time know better. If human civilization disappeared tomorrow, what would remain after 1 million years? After 10 million years? After 100 million years? Most of our buildings would crumble and decay. Our roads would be covered by forests, and then by geological layers. Our metal tools would rust away. Even our bones would likely dissolve in soil and water. The vast majority of everything we have created would vanish without a trace. Some things might survive longer, perhaps some stone monuments in very stable locations. Certainly, some of our industrial activities have changed the chemistry of Earth's atmosphere and oceans in ways that might be detectable millions of years from now. But these would be subtle traces requiring very sophisticated analysis to discover. So if we can barely expect our own civilization to leave lasting traces in deep time, how could we hope to find evidence of civilizations that existed millions or hundreds of millions of years ago? This is both the challenge and the fascination of our question. We are looking for traces of something that may have been deliberately erased by the slow, patient work of geological time. We are asking whether there might be subtle signatures hidden in rocks and sediments that could tell us about forms of intelligence that existed long before humans appeared. Some scientists have begun looking for exactly these kinds of traces. They search for unusual patterns in ancient rocks that might indicate large scale environmental changes caused by intelligent activity. They look for chemical signatures that might suggest industrial processes or large scale agriculture or other activities that could only come from organized intelligent life. So far, these searches have not found clear evidence of ancient civilizations, but they have taught us something equally important. They have shown us how difficult it would be to detect such civilizations, even if they had existed. The absence of evidence is not evidence of absence, especially when we are looking across such vast scales of time. As we continue our exploration together over the coming chapters, we will look more closely at how Earth preserves and erases its history. We will examine the few traces that do survive from the deep past and consider what they might tell us. We will explore the various ways that civilizations might arise and the different forms they might take. We will journey through underwater archaeological sites that hint at human settlements lost to rising seas. We will visit ancient megalithic monuments that demonstrate sophisticated knowledge and engineering. We will consider the great cycles of climate and geology that have shaped our planet's surface again and again. Most importantly, we will try to maintain a sense of wonder and humility as we explore these questions. Science at its best is not about finding definitive answers, but about asking better questions. It is about remaining curious and open to possibilities, while still being careful and rigorous in our thinking. The question of whether we are the first civilization on Earth may never have a final answer, but exploring it teaches us something valuable about our planet and our place in the vast story of life. It reminds us that we are part of something much larger and longer than human history. It invites us to think about intelligence and civilization in broader ways. Tonight, as you drift towards sleep, you might carry this question with you gently. Let your mind wander through the vast landscapes of deep time. Imagine the countless experiments in living that have played out on this planet over billions of years. Wonder about the forms of intelligence and creativity that might have emerged and disappeared long before our own species appeared. There is something both humbling and comforting about placing ourselves in this larger context. We are not separate from the long story of life on Earth. We are part of it. And perhaps somewhere in that story, hidden in layers of rock and time, there are traces of other minds that once wondered about their place in the cosmos, just as we do now. In our next gentle exploration, we will begin to look more closely at how Earth keeps its records. We will discover how rocks and sediments preserve some stories while erasing others. We will learn about the great library of stone that surrounds us and consider what ancient secrets it might hold. Until then, rest well knowing that you are part of a story much larger and more mysterious than any of us can fully comprehend. And perhaps that is exactly as it should be. We are going to learn about how Earth keeps its records, how it preserves some stories while letting others fade away completely. Think of this as discovering a library unlike any other, a library made of stone and sediment that has been collecting stories for billions of years. This library does not organize its information the way we might expect. It does not keep everything in neat categories or preserve materials equally well. Instead, it follows its own ancient rules about what survives and what disappears. Understanding these rules helps us appreciate both what we can learn from the past and what we might never know. Every layer of rock beneath your feet tells a story. These layers formed over millions of years as sand and mud and tiny pieces of life settled slowly to the bottom of ancient seas and lakes and rivers. Grain by grain, these materials built up into the sedimentary rocks that now hold most of the fossils we find. Imagine a quiet lake millions of years ago. Day after day, tiny particles drift down through the water. Dead plants and animals sink to the bottom. Mud washes in from nearby hills. Very slowly, this lake bed builds up layer upon layer. Each layer captures a moment in time, like a photograph made of sediment. Over thousands of years, these soft layers harden into rock. The organic materials trapped inside sometimes become fossils. The patterns in the rock preserve information about ancient climates and environments. The chemistry of the minerals holds clues about what the atmosphere and oceans were like long ago. But this natural library is very selective about what it preserves. Some materials survive the long journey through geological time, while others disappear almost immediately. Understanding what survives and what does not is crucial for our exploration of possible ancient civilizations. Hard materials like bones and shells have the best chance of becoming fossils. The minerals in these structures can be slowly replaced by other minerals without losing their original shape. This is why we have so many fossils of dinosaur bones and ancient sea creatures with shells. These materials were already partly mineral when the organisms were alive. Stone tools made by early humans sometimes survive for millions of years. The same qualities that made stone useful for making tools also make it likely to survive in the geological record. A carefully shaped piece of flint can remain almost unchanged even after being buried and compressed for enormous spans of time. But most of the materials that civilizations use disappear much more quickly. Wood rots away within decades or centuries unless it is preserved in very special conditions. Fabric and paper and leather break down even faster. Most metals rust and corrode, leaving behind only traces that are difficult to detect. Think about what this means for our question about ancient civilizations. If an intelligent species had developed sophisticated technology millions of years ago, what evidence might remain? If they built with wood and plant fibers and organic materials, almost nothing would survive. If they used metals extensively, we might find only subtle chemical traces in certain rocks. Even more challenging is the fact that organic materials from living things are exactly the kinds of materials that Earth recycles most efficiently. The carbon in ancient trees becomes part of new trees. The calcium in old bones gets dissolved and becomes part of new shells and bones. The nitrogen in decaying bodies feeds new plants. This recycling is one of the reasons life on Earth has been able to continue for billions of years. The fossil record that we do have represents only a tiny fraction of all the life that has ever existed. Scientists estimate that we have fossils from less than 1% of all the species that have lived on Earth. For most types of organisms, the preservation rate is much lower than that. Consider how rarely the soft tissues of animals are preserved. We have thousands of dinosaur skeletons, but only a handful of fossils that show dinosaur skin or internal organs. We have countless shells from ancient sea creatures, but very few fossils that show what the soft animals inside those shells looked like. This means that most of what ancient life forms actually did and how they lived remains invisible to us. We see the hard, durable parts, but miss most of the behavior and soft anatomy and complex interactions that made these creatures what they were. If preservation is so difficult for simple biological materials, imagine how much harder it would be to find traces of technology or culture, or the kinds of activities that we associate with civilization. A wooden tool disappears much faster than a bone. A woven basket degrades much more quickly than a shell. The everyday objects that civilizations create and use are usually made from exactly the kinds of materials that the geological record preserves least well. Yet sometimes the Earth surprises us with extraordinary preservation. In certain rare conditions, organic materials can survive for millions of years. Insects trapped in amber are preserved in perfect detail, including their internal organs and even the contents of their stomachs. Some amber specimens are over 100 million years old, yet the creatures inside look as if they died yesterday. Occasionally, we find fossils that preserve soft tissues like skin or muscle or even internal organs. These discoveries are so rare and so unexpected that each one makes headlines in scientific journals. They show us that under just the right conditions, almost anything can be preserved. Ice can preserve organic materials for thousands of years. We have found perfectly preserved mammoths in the frozen ground of Siberia. Their meat was so well preserved that scientists have been able to study their DNA and even their last meals. Dry environments can also preserve organic materials much longer than usual. In some desert caves, archaeologists have found textiles and wooden tools that are thousands of years old. The absence of moisture prevented the normal processes of decay from destroying these fragile materials. These examples of exceptional preservation give us hope that traces of ancient civilizations might still exist somewhere waiting to be discovered. But they also remind us how unusual such preservation really is. For every perfectly preserved insect in amber, there were billions of other insects whose remains vanished completely. The chemical traces of life can sometimes survive even when all the physical structures have disappeared. Scientists can detect biological molecules in rocks that are billions of years old. These chemical fossils tell us about ancient life forms that left no other trace of their existence. Could similar chemical traces preserve evidence of ancient technology? Perhaps. Industrial processes create distinctive chemical signatures. Large-scale agriculture changes the chemistry of soils. Even the burning of fires leaves traces that can be detected in certain circumstances. Some scientists have begun looking for exactly these kinds of chemical signatures in ancient rocks. They search for unusual concentrations of rare metals that might indicate mining or refining activities. They look for isotope ratios that might suggest large-scale combustion or other industrial processes. So far, these searches have not found convincing evidence of ancient industrial civilizations, but they have shown us how difficult such evidence would be to detect and how easily it could be missed or misinterpreted. The absence of obvious traces does not necessarily mean that ancient civilizations never existed. As we read the story written in stone, we must remember that it is an incomplete story. Whole chapters are missing. Many of the most interesting details have been erased by time. What we can read is fascinating, but it represents only a small sample of everything that has happened on our planet. This teaches us something important about the search for ancient civilizations. We should not expect to find obvious evidence like ruins or artifacts. Instead, we should look for subtle traces that might have survived the slow recycling of Earth's surface, we should remain open to the possibility that evidence exists in forms we have not yet learned to recognize. The story written in stone is also constantly being rewritten. New layers form on top of old ones. Existing rocks are heated and compressed until they change into different types of rock entirely. The movements of continents carry rocks from one environment to another where different processes affect them. This means that evidence of ancient civilizations might exist in some places, but not in others. It might be preserved in certain types of rock, but destroyed in others. The search for such evidence requires understanding not just what to look for, but where and how to look for it. As we continue our journey together, we will explore what this means for the possibility of finding traces of civilizations that existed long before humans appeared. We will look at underwater archaeological sites where recent human settlements have been preserved by rising seas. We will visit ancient monuments that demonstrate sophisticated knowledge and engineering. But first, let us appreciate the remarkable library of stone that surrounds us. Every rock has a story to tell about the deep past. Every fossil is a message from forms of life that lived and died millions of years ago. Every chemical trace is a clue about conditions and events that shaped our planet long before we were here to witness them. Tonight, as you settle toward sleep, you might think about the ground beneath your feet. Imagine the layers of story slowly accumulating over millions of years. Picture the ancient lakes and seas where these stories were first written. Consider the countless forms of life that contributed their traces to this vast geological library. Rest knowing that you are part of this continuing story. Someday the traces of our own civilization will join the layers of rock that tell the story of Earth. Future beings might puzzle over our chemical signatures, just as we puzzle over the traces left by life forms that came before us. In our next gentle exploration, we will travel backward to a time when the world looked very different. We will visit the end of the last ice age, when vast amounts of water were locked up in glaciers, and the sea levels were much lower than they are today. Now we move forward through time at a more familiar pace. We are going to explore a period that ended just 12,000 years ago, a time when the world looked remarkably different than it does today. This is the story of the last ice age and what happened when it finally came to an end. It is a story about rising seas and vanishing lands, and the possibility that evidence of early human settlements now lies hidden beneath the waves. It is also a story that might help us understand how Earth could hide traces of much older civilizations. 12,000 years ago, massive sheets of ice covered much of North America and Northern Europe. These glaciers were not like the ice we see in freezers, or even like the ice sheets that exist today in Antarctica and Greenland. They were enormously thick layers of ice that stretched across entire continents. Imagine ice 2 kilometers thick, covering the places where cities like New York and London now stand. Picture glaciers extending from the Arctic Ocean all the way down to where the modern borders between countries now run. These ice sheets held so much water that the level of the oceans around the world was much lower than it is today. Scientists believe that during the peak of the last ice age, sea levels were about 120 meters lower than they are now. That is like looking down from the top of a 40-story building. It is enough to completely change the shape of continents and reveal vast areas of land that are now underwater. With sea levels so much lower, the world map looked very different. Britain was not an island, but part of a larger landmass connected to mainland Europe. A broad plain called Doggerland stretched between what we now call England and the Netherlands and Denmark. You could have walked from London to Paris without ever seeing the ocean. Australia and New Guinea were joined into a single large continent. The islands of Southeast Asia were connected by land bridges. The Bering Strait between Alaska and Siberia was dry land, allowing people and animals to walk between Asia and North America. These lower sea levels exposed enormous areas of what we now call the continental shelf. These are the relatively shallow underwater areas that extend outward from modern coastlines before dropping off into the deep ocean. During the Ice Age, much of this continental shelf was dry land with its own rivers and lakes and forests. People living during this time would naturally have been attracted to these coastal areas. River mouths and coastlines provide some of the richest environments for human settlement. They offer fresh water from rivers and abundant food from both the land and the sea. The climate near coastlines is often more moderate than in inland areas. Archaeological evidence suggests that early humans did indeed prefer to live in these coastal regions. Some of our most important early settlements have been found in areas that were near ancient coastlines. The problem is that many of these ancient coastlines are now deep underwater. As the Ice Age gradually came to an end, the massive glaciers began to melt. This happened slowly over thousands of years, but the effects were dramatic. All that water trapped in the vase returned to the oceans, causing sea levels to rise steadily. The rich coastal plains where people had lived for thousands of years began to disappear beneath the waves. This was not a sudden catastrophic flooding like what we might see in movies. Instead, it was a gradual process that took place over many generations. The sea level rose, perhaps a few centimeters per year. People living near the coast would have noticed that beaches were slowly shrinking and that areas that had once been dry land were becoming marshy and then permanently flooded. Over centuries and millennia, this gradual flooding transformed the geography of the entire world. Doggerland slowly became a series of islands and then disappeared entirely beneath what we now call the North Sea. The land bridges connecting continents were submerged. Coastal plains that had supported human communities for thousands of years vanished under hundreds of feet of water. What this means is that much of the evidence for early human civilization now lies on the ocean floor. The areas where people were most likely to build permanent settlements and develop complex societies are exactly the areas that are now underwater. If we want to understand the full story of human development, we need to look beneath the waves. Marine archaeologists have begun to do exactly this. Using underwater robots and sophisticated sonar mapping, they have discovered traces of ancient human settlements on the ocean floor. These discoveries are changing our understanding of how and where early civilizations developed. Off the coast of India, archaeologists have found what appears to be the remains of a large ancient city. Local legends speak of the city of Dwarka, which according to Hindu texts was a magnificent city that was eventually swallowed by the sea. The underwater structures that have been discovered match many of the descriptions in these ancient texts. In the Mediterranean Sea, underwater archaeologists have found complete ancient settlements with houses and streets and harbors all perfectly preserved beneath the waves. These towns were inhabited thousands of years ago when sea levels were lower. As the water rose, the inhabitants gradually moved to higher ground, leaving their old settlements to be claimed by the sea. The most extensive underwater archaeological site discovered so far is probably Doggerland itself. Fishing boats working in the North Sea regularly bring up tools and bones and other artifacts from the sea floor. These discoveries paint a picture of a rich landscape that was home to both humans and animals for thousands of years. Scientists have used sonar mapping to create detailed pictures of what Doggerland looked like when it was above water. They have found the courses of ancient rivers and the locations of ancient lakes. Some areas appear to have supported large forests, while others were open grasslands, perfect for hunting. The artifacts recovered from Doggerland include sophisticated stone tools and weapons. There are also remains of the animals that lived there, including mammoths and wild horses, and many species that are now extinct. This evidence suggests that Doggerland supported a complex ecosystem and possibly quite advanced human societies. But Doggerland represents only a small fraction of the land that was submerged when the Ice Age ended. Similar coastal plains existed around every continent. Each of these areas potentially contains evidence of early human settlement that we have not yet discovered. Consider the continental shelf around North America, or South America, or Africa, or Asia. All of these areas were dry land 12,000 years ago. All of them would have been attractive places for human settlement, and all of them are now underwater, often beneath hundreds of feet of water and sediment. The techniques needed to explore these underwater archaeological sites are expensive and technically challenging. It is much harder to excavate underwater than on dry land. Many areas of the ocean floor are covered by thick layers of sediment that have accumulated over thousands of years. Finding and uncovering ancient settlements requires specialized equipment and expertise. This means that we have probably discovered only a tiny fraction of the underwater archaeological sites that exist. Vast areas of the ocean floor remain unexplored. There could be thousands of ancient settlements waiting to be discovered beneath the waves. What makes this even more interesting for our larger question about ancient civilizations is that it shows how easily evidence of human activity can disappear. The settlements now underwater were inhabited by people just a few thousand years ago. Yet without modern technology, we would never know they existed. If rising seas can hide evidence of human civilization from just a few thousand years ago, imagine how much more evidence might be hidden by the much longer processes of geological change. If sea level changes over thousands of years can submerge entire landscapes, what might continental drift and mountain building accomplish over millions of years? The story of post-Ice Age flooding also shows us that major changes to Earth's surface happen on timescales that are much longer than human memory, but much shorter than geological time. 12,000 years is a long time by human standards, but it is just a moment in Earth's history. During this relatively short period, entire continents changed shape, and thousands of square kilometers of inhabited land disappeared forever. If such dramatic changes can happen so quickly in geological terms, it becomes easier to imagine how evidence of much older civilizations might have been erased entirely. The gradual nature of these changes is also important to consider. The people living through the end of the Ice Age probably did not realize they were witnessing one of the most dramatic transformations in Earth's recent history. To them, it was simply a fact of life that the sea was slowly rising and that they needed to move their settlements to higher ground from time to time. This suggests that major geological changes might often be invisible to the people and civilizations experiencing them. A slowly sinking continent or a gradually shifting climate might be adapted to generation by generation without anyone realizing that their world is fundamentally changing. As we continue our exploration, we will dive deeper beneath the waves to examine some of the most mysterious underwater discoveries that have been made so far. We will visit sites that challenge our understanding of what early human civilizations were capable of accomplishing, and we will consider what these discoveries might tell us about the possibility of finding evidence of much older civilizations. Tonight, as you rest, think about the vast landscapes that lie hidden beneath the oceans. Imagine walking across Doggerland when it was a green and fertile plain dotted with lakes and crossed by rivers. Picture the communities that lived there and wonder about the stories they told and the knowledge they accumulated. Consider how the gradual rise of the seas must have seemed to the people experiencing it. Perhaps they thought it was temporary. Perhaps they believed their children would see the waters recede. They could not have imagined that their homeland would disappear forever beneath the waves. Rest knowing that the ocean floors hold secrets from our own species, recent past, and possibly from much deeper in time as well. The waters that seem so permanent and unchanging were actually the keepers of hidden landscapes and vanished worlds. Tomorrow, we will explore what other mysteries might be waiting in the depths. And now we turn our attention beneath the waves to a world of sunken cities and hidden structures that hint at ancient knowledge. Across the globe, marine archaeologists have discovered underwater sites that challenge our understanding of early human capability and perhaps much older mysteries too. Off the coast of Japan, divers found the Yonaguni Monument. At first glance, it looks like a natural rock formation, but closer study reveals flat plains, right angles, and straight lines that suggest human shaping. Is it a submerged temple or a curious quirk of geology? Scientists continue to debate, gently weighing the evidence without rushing to sensational conclusions. Far to the west, in the Bahamas, lies the Bimini Road. Here, long linear stone formations lie just beneath shallow water. They form a path that stretches for hundreds of meters. Some believe these stones were arranged by an ancient people. Others think they are the fractured remains of natural limestone layers. The truth remains elusive, but the calm mystery invites us to ponder. In India, off the coast of Dwarka, sonar images revealed the outlines of streets, walls, and buildings under 20 meters of water. Local legends speak of a grand city built by a divine king, swallowed by the sea. Excavations have unearthed stones carved with sculptures and tools that match descriptions from ancient texts. While debate continues, these finds remind us how the sea can conceal human history. The Mediterranean Sea, cradle of early civilizations, holds its own underwater treasures. In the waters off Greece, the ruins of Pavlopetri lie untouched for 5,000 years. Here we see houses, courtyards, and even tombs preserved in perfect layout. In Turkey, near the ancient city of Kekova, submerged walls and towers stand as silent witnesses to a world lost to rising seas. These underwater sites share common challenges. Ocean currents shift sand and silt, sometimes burying or exposing structures over time. Marine life encrusts surfaces, blending stone and sea into a living tapestry. Excavation must be done with delicate care to avoid disturbing fragile remains, yet each discovery offers a rare glimpse into past worlds. The presence of such sites shows us how easily entire settlements can vanish from sight. Coastal communities that thrived for centuries could be lost within a few generations as the sea crept inland. Their stories, tools, and buildings now lie hidden beneath waves that we often take for granted. As we consider these underwater mysteries, we also reflect on our larger question: if human settlements from just a few thousand years ago can be so thoroughly concealed, what might we miss from civilizations that existed millions of years earlier? What subtle traces might be hidden in rocks and sediments far below modern sea level? Tonight, as you drift towards sleep, imagine yourself diving beneath calm waters to explore sunken streets and half-buried walls. Picture stone blocks carved with care, now home to colorful corals and gentle fish. Think about the hands that shaped those stones and the people who once walked among them. Rest knowing that the oceans guard countless secrets. Some will be revealed slowly by careful study and patient exploration. Others may remain forever out of reach, their stories erased by time. Yet even in this uncertainty, there is beauty and wonder. The sea invites us to keep asking questions and to remain open to the mysteries that lie beneath its surface. Let us now turn our gaze to the land, where ancient people built with stone. Across every continent, massive monuments of rock stand as silent witnesses to human curiosity and skill, though they vary in name and style. Stone circles, dolmens, passage tombs, they share a common trait: careful placement of huge stones that required clever planning and cooperation. Imagine Stonehenge on the windswept plains of England. Massive upright stones ring a central circle, aligned so that on a midsummer sunrise, the light flows through the stones in perfect symmetry. Scientists think its builders understood the cycles of the sun and seasons well enough to mark them in stone. They worked together to move these stones, some weighing more than 20 tons, from miles away using simple tools and ingenious methods. Thousands of miles to the east lies Göbekli Tepe in modern Turkey. Here, round enclosures of carved pillars date back more than 11,000 years, older than Stonehenge by millennia. Each pillar stands upright in a circle, decorated with carved animals and abstract symbols. No one knows exactly how this site was used, but its sophistication shows that complex social organization existed long before cities and writing appeared. In Ireland, the tomb of New Grange greets the winter solstice sunrise. A narrow passage leads into a stone chamber, deep within a man-made mound. At dawn on the shortest day of the year, sunlight travels through that passage to illuminate the chamber's interior for a few magical moments. This precise alignment required careful observation of the sun's path and proof that these builders recorded and applied that knowledge across generations. Half a world away on Easter Island, the Moai stand watch over rolling grasslands. These giant statues, some more than 10 meters tall, were carved from volcanic rock and then moved many kilometers to their resting places. Each Moai sits upon a stone platform called an ahu, facing inland to look over the island's communities. The work of carving and moving these giants required not only strength, but shared purpose and communication. Further beyond, in the highlands of Bolivia, Pumapunku reveals stone blocks cut with astonishing precision. Some blocks interlock like puzzle pieces, with smooth surfaces and right angles far beyond what simple stone tools usually achieve. How these stones were cut and moved remains a mystery, but it speaks of deep knowledge of geometry and stonecraft. What do these sites tell us about ancient humans? They show that people everywhere sought to connect with the sky and the land, to mark time and express ideas in lasting form. They remind us that human ingenuity and cooperation can shape the world in remarkable ways. Yet these megaliths are also fragile. In deep time, weathering and erosion slowly wear down their carved edges. Plant roots pry apart joints, stones topple, and fragments scatter. Many sites have been lost or buried, while those that remain survive only because they were built of the toughest rock and in places less prone to change. If humanity's greatest stone monuments can fade away over centuries and millennia, what might happen to monuments built of softer materials? Wooden temples, woven banners, metal sculptures, all would disappear far sooner, leaving behind only subtle traces in soil and sediment. As you drift towards sleep tonight, picture these silent stones under moonlight. Imagine standing among the towering pillars of Göbekli Tepe, or feeling the cold ancient air inside Newgrange's tomb. Think of societies united by common purpose, building monuments that connect earth and sky. Rest knowing that these stones carry stories of human hope and wonder. Their presence reminds us of our own potential and our vulnerability, how even the grandest creations yield to time's gentle hand, and in their slow decay, they teach us humility as we ponder what traces our own civilization might leave behind. As we journey deeper into Earth's story, we encounter one of the most profound patterns in the history of life. It is a pattern of endings and beginnings, of catastrophic loss, followed by remarkable renewal. We are going to explore the great extinction events that have punctuated Earth's history and consider what they might mean for our question about ancient civilizations. Throughout the vast span of geological time, life on Earth has faced 5 major mass extinctions. These were not gradual changes, but relatively sudden events that swept away large portions of the living world. Each extinction reshaped the entire fabric of life on our planet, clearing the stage for entirely new forms of existence to emerge. The most recent and famous of these extinctions happened 66 million years ago. This is the event that ended the age of dinosaurs, though it affected far more than just those magnificent reptiles. Scientists believe a massive asteroid struck Earth near what is now the Yucatan Peninsula in Mexico. The impact created a crater more than 100 kilometers wide and threw enormous amounts of dust and debris into the atmosphere. The immediate effects were catastrophic. The sky darkened for months as particles blocked sunlight. Plants could not photosynthesize properly. Food chains collapsed from the bottom up. Large animals, including most dinosaurs, simply could not find enough to eat. Within a relatively short time, perhaps just a few thousand years, about 75% of all species on Earth disappeared forever. But this was not the largest extinction event in Earth's history. That distinction belongs to an event that occurred 252 million years ago at the boundary between the Permian and Triassic periods. Scientists call this the Great Dying, and it was far more severe than the extinction that ended the dinosaurs. During the Great Dying, massive volcanic eruptions in what is now Siberia poured lava across an area larger than Europe. These eruptions continued for thousands of years, releasing enormous amounts of carbon dioxide and other gases into the atmosphere. The climate warmed dramatically. Ocean chemistry changed. Acid rain fell from poisoned skies. The results were almost unimaginable. Scientists estimate that 96% of marine species went extinct on land. About 70% of vertebrate species disappeared. Life came closer to complete extinction than at any other time in Earth's history. For millions of years afterward, ecosystems remained simple and sparse as the few survivors slowly began to rebuild the diversity of life. Between these two famous extinctions lie three others, each with its own character and causes. The Ordovician extinction 445 million years ago was likely caused by ice ages that dramatically lowered sea levels. The Devonian extinction 375 million years ago may have resulted from changes in ocean chemistry that depleted oxygen levels. The Triassic extinction 200 million years ago cleared the way for dinosaurs to become dominant. What makes these extinction events so important for our exploration is not just their destructive power, but what happened afterward. In every case, life not only recovered, but diversified in entirely new directions. The extinctions acted like great clearings in a forest, removing the dominant species and allowing previously minor forms of life to expand and experiment. After the Great Dying, for example, the few surviving species found themselves in a world with endless opportunities. Ecological niches that had been occupied for millions of years were suddenly empty. Over the following millions of years, these survivors evolved into entirely new forms. The age of reptiles began. Eventually, this recovery led to the evolution of dinosaurs, mammals, and countless other groups that would define life for the next 200 million years. This pattern of recovery and diversification is one of the most remarkable aspects of life on Earth. No matter how severe the extinction, life finds ways to persist and then to flourish again. The forms that emerge are often completely different from what existed before. Evolution seems to be endlessly creative, finding new solutions to the challenges of survival. Intelligence appears to be one of these evolutionary solutions. It has emerged multiple times in Earth's history, in different groups and in different forms. Mammals developed complex brains and social behaviors. Birds, which are dinosaur descendants, show remarkable problem-solving abilities. Cephalopods, like octopuses, evolved intelligence along a completely different path from vertebrates. This repeated emergence of intelligence raises fascinating questions for our exploration. If intelligence can evolve multiple times in the relatively recent past, could it have evolved much earlier as well? Could there have been intelligent species that flourished during the long periods between extinction events, only to vanish when the next catastrophe struck? Consider the vast stretches of time involved. The Permian period before the Great Dying lasted about 47 million years. That is more than enough time for intelligence to evolve, develop complex societies, and even create technologies. If such a civilization had existed, would we be able to detect it today? The challenge is that extinction events are followed by millions of years of geological activity that can erase or bury evidence. New sediments are deposited, old rocks are weathered away. The very processes that allow life to recover also work to hide traces of what came before. Moreover, the recoveries after mass extinctions involve dramatic reorganization of ecosystems. New types of environments appear, different patterns of sedimentation begin. The geological record itself changes character, making it even harder to preserve or detect traces of pre-extinction life. This does not mean that evidence of ancient civilizations would necessarily be lost, but it does suggest that such evidence would be extremely difficult to find and recognize. It would be buried beneath layers of rock that represent millions of years of post-extinction recovery and change. The extinction events also remind us how fragile complex life can be. Even the most successful and widespread species can vanish relatively quickly when conditions change. The dinosaurs ruled the Earth for over 160 million years, far longer than humans have existed. Yet they were still vulnerable to sudden environmental catastrophe. This vulnerability applies to intelligence and civilization as well. A species might develop sophisticated technology and complex societies, but still be unable to survive a major extinction event. Their achievements would be buried beneath the geological evidence of the catastrophe that destroyed them and the subsequent recovery of life. The study of mass extinctions has taught scientists something else important about the history of life. Recovery is not just about surviving species, adapting to new conditions. It is also about the evolution of entirely new forms of life that take advantage of the opportunities created by extinction. In some cases, these new forms develop capabilities that did not exist before the extinction. The mammals that inherited the Earth after the dinosaurs developed larger brains and more complex behaviors than their predecessors. Birds evolved sophisticated navigation abilities and social structures. Each recovery phase seems to push life in new directions. This suggests that intelligence itself might be more likely to evolve after extinction events, when ecological opportunities are abundant and evolutionary pressures favor innovation and adaptability. If so, the periods following each of the 5 great extinctions might have been particularly favorable for the development of intelligent species. We are currently living through what many scientists consider the 6th mass extinction. Human activities are causing species to disappear at rates that rival or exceed those of the great extinction events of the past. This modern extinction raises profound questions about our own future and the future of intelligence on Earth, but it also provides a perspective on our larger question about ancient civilizations. If our own civilization were to disappear in this 6th extinction, what traces would remain for future archaeologists to discover? And if we can barely expect our own advanced civilization to leave clear evidence, how much harder would it be to find traces of civilizations that vanished in earlier extinction events? The great extinctions teach us that life on Earth has always been subject to sudden dramatic changes. Species that seem dominant and permanent can vanish within geological moments, but they also teach us that life is remarkably resilient and creative. After every catastrophe, new forms of life emerge, often more complex and capable than what existed before. As we consider the possibility of ancient civilizations, we must keep both of these lessons in mind. Intelligence and civilization might have evolved multiple times in Earth's long history, but the same processes that clear the way for new forms of life also work to erase evidence of what came before. Tonight, as you drift towards sleep, imagine the great cycles of loss and renewal that have shaped our planet. Picture the silent world after a mass extinction, gradually coming back to life as new species emerge and spread. Think about the countless experiments in living that have played out over hundreds of millions of years. Consider that we ourselves are part of this great story. We are products of the recoveries that followed ancient catastrophes. Our own intelligence evolved in the aftermath of the extinction that ended the dinosaurs. We carry within us the legacy of all the survivors who persisted through Earth's darkest moments and then flowered into new forms of life. Rest knowing that this pattern of renewal gives us hope even as it teaches us humility. Life finds a way to continue, to grow more complex, to explore new possibilities. Whether or not other intelligences have walked this path before us, we are proof that the universe can know itself through conscious minds that wonder about their place in the cosmic story. In our next gentle exploration, we will turn to the stories that humans have told about lost civilizations and ancient floods. We will discover how myths and legends from around the world might preserve memories of real events, and consider what these stories might tell us about our deep past and our enduring fascination with the possibility of those who came before us. To boldly enter a different kind of exploration, we move from the world of rocks and fossils into the realm of human memory and storytelling. Tonight, we will listen to the echoes of ancient myths and consider whether these old stories might preserve traces of real events from our deep past. Across every culture on Earth, people have told stories about great floods that once covered the world. These are not recent tales, but some of humanity's oldest narratives, passed down through countless generations. The similarities between these stories from distant cultures are striking, even though the peoples who told them had no contact with each other for thousands of years. In the Middle East, the Epic of Gilgamesh tells of Utnapishtim, who built a great boat to survive a flood sent by the gods. This story was already ancient when it was first written down in cuneiform script more than 4,000 years ago. The Hebrew Bible tells a similar tale of Noah and his ark, preserving pairs of animals through a worldwide deluge that lasted 40 days and 40 nights. But flood stories are not limited to the Middle East. Hindu texts describe Manu, who was warned by the god Vishnu to build a boat before a great flood destroyed the world. In Greek mythology, Deucalion and Pyrrha survived a flood sent by Zeus to cleanse the earth of wickedness. The survivors repopulated the world by throwing stones behind them, which became new people. Indigenous peoples of the Americas have their own flood traditions. The Ojibwe tell of Nanaboso, who survived a great flood by climbing to the top of a tall tree and then recreated the world with the help of animals. Aztec mythology speaks of multiple worlds destroyed by floods and other catastrophes. From the Pacific Northwest to the Amazon basin, Native American cultures preserved stories of waters rising to cover the land. Even in Australia, Aboriginal Dreamtime stories speak of great floods that reshape the landscape. Some of these stories describe specific geographical features and seem to match what scientists know about rising sea levels at the end of the last ice age. The precision of these accounts has surprised researchers who study the relationship between myth and geological history. What are we to make of these remarkably similar stories from around the world? One possibility is that they represent universal human fears about natural disasters. Floods are common experiences in many environments, and it would be natural for people to imagine truly catastrophic versions of familiar events. Another interpretation suggests that these stories might preserve actual memories of real floods that occurred thousands of years ago. As we learned in our earlier exploration, the end of the last ice age involved dramatic rises in sea level that flooded vast coastal areas where early humans lived. Perhaps the flood myths are cultural memories of these real events, transmitted through oral tradition across many generations. The most famous story of a lost civilization comes from the ancient Greek philosopher Plato. Around 2,400 years ago, he wrote about Atlantis, a powerful island civilization that supposedly existed 9,000 years before his own time. According to Plato, Atlantis was a marvel of engineering and architecture, with concentric rings of canals and magnificent temples dedicated to the sea god Poseidon. But Atlantis became corrupt and aggressive. Plato wrote, the gods decided to punish this civilization by destroying it in a single day and night of earthquakes and floods. The entire island sank beneath the waves, leaving no trace except the memory preserved in ancient Egyptian records that Plato claimed to have accessed. Most scholars believe that Plato invented Atlantis as a philosophical allegory, a way of exploring ideas about ideal societies and the dangers of power and corruption. But the story has captured imaginations for over 2 millennia, inspiring countless expeditions and theories about where this lost civilization might have existed. Plato was not the only ancient writer to describe vanished civilizations. Later authors wrote about Lemuria, a supposed continent in the Indian Ocean, and Moa, said to have existed in the Pacific. These stories often mix genuine geographic knowledge with speculation and imagination, creating compelling narratives that blurred the line between history and myth. What makes these stories particularly interesting for our exploration is how they might preserve fragments of real information about the past, even when the overall narrative is fictional or symbolic. Oral traditions are remarkably good at preserving certain types of information across many generations, especially stories that have emotional importance or practical value. Indigenous Australian cultures provide some of the best examples of how oral tradition can preserve accurate information about ancient events. Some Aboriginal stories describe the flooding of specific valleys and the formation of particular islands. When scientists study the geological history of these areas, they find that the stories match what actually happened thousands of years ago when sea levels rose at the end of the Ice Age. Similarly, some Native American stories describe the bursting of ice dams that created massive floods in specific regions. Archaeological and geological evidence confirms that such events did occur, suggesting that these stories preserve accurate memories of real geological events that happened over 10,000 years ago. This ability of oral tradition to preserve factual information raises intriguing questions. If stories can accurately remember geological events from 10,000 years ago, might they also preserve information about human societies that existed during those distant times? Could some flood myths contain memories of actual civilizations that were lost when sea levels rose? The challenge is learning to distinguish between the factual core of a story and the symbolic or mythological elements that may have been added over time. Stories change as they are retold, details are added, removed, or modified to serve the needs of each generation that tells them. What begins as a straightforward account of real events can gradually transform into something quite different. Yet even transformed stories may preserve important clues. The widespread nature of flood myths suggests that they reflect some common human experience, whether literal floods or symbolic representations of dramatic change and renewal. The consistent themes of survival, rescue, and rebuilding hint at real psychological and perhaps historical patterns. Some researchers have suggested that flood myths might preserve memories not just of rising sea levels, but of other catastrophic events in human history. Massive volcanic eruptions, asteroid impacts, or sudden climate changes could all create the kinds of dramatic disruptions that might be remembered as great floods that destroy the world and require it to be rebuilt. The tsunami that struck the Indian Ocean in 2004 provides a modern example of how such events can become embedded in cultural memory. Communities that experienced the disaster immediately began developing stories and rituals to help make sense of what happened and to preserve important survival knowledge for future generations. If a tsunami can have such powerful effects on cultural memory, imagine the impact of truly global catastrophes, like those that might have accompanied major extinction events or dramatic climate shifts. Such events could easily become the basis for stories about world destroying floods and the few survivors who preserved life and knowledge through the catastrophe. The psychologist Carl Jung proposed that certain story patterns might be inherited rather than learned, passed down through what he called the collective unconscious. Jung argued that all humans share certain archetypal stories and symbols that reflect universal aspects of human experience. From this perspective, flood myths might represent not memories of specific events, but deeper psychological patterns about death, rebirth, and the cyclical nature of existence. Whether we interpret them as literal history, symbolic truth, or psychological archetypes, flood myths and stories of lost civilizations reveal something important about human nature. We are storytelling creatures who use narratives to make sense of our world and our place in it. We are drawn to stories about those who came before us, especially those who might have achieved great things only to lose them to the forces of time and change. These stories also reflect our awareness that civilizations are fragile and temporary. Even when ancient peoples did not understand geological timescales or the scientific details of extinction events, they intuited that great changes could sweep away entire ways of life. Their myths express both the fear of such losses and the hope that something essential might survive to continue the human story. As we consider the possibility of ancient civilizations that existed long before human history began, these mythological traditions offer both inspiration and caution. They remind us that the boundary between memory and imagination is often unclear and that extraordinary claims require extraordinary evidence. Yet they also suggest that the human fascination with lost civilizations runs very deep. Purists, this fascination reflects not just our love of mystery and adventure, but also our intuitive understanding that intelligence and culture have likely emerged many times in Earth's long history. Our myths may not preserve literal memories of pre-human civilizations, but they express our deep sense that we are part of a much larger and older story than written history can tell. Tonight, as you settle into sleep, you might think about the stories your own ancestors told around fires on dark nights. Consider how those tales mixed memory and imagination, fear and hope into narratives that help make sense of an uncertain world. Picture the countless generations of storytellers who preserved and transformed these tales, each adding their own understanding to the collective memory of their people. Rest knowing that you are part of this ancient tradition of storytelling and wondering. The questions we are exploring together about ancient civilizations connect us to the deepest human need to understand our origins and our place in the vast story of life on Earth. Whether or not previous civilizations existed, our willingness to imagine them reveals something beautiful about human consciousness and its endless curiosity about what lies hidden in the depths of time. In our next gentle exploration, we will turn from myth to science as we examine a fascinating thought experiment called the Silurian Hypothesis. We will discover what modern researchers have learned about how civilizations leave traces in the geological record, and we will consider what this means for our search for evidence of ancient intelligence on Earth. Now we leave the realm of ancient stories and enter the careful world of scientific investigation. We are going to explore a fascinating thought experiment that has captured the attention of researchers around the globe. It is called the Silurian Hypothesis, and it asks a deceptively simple question. If an industrial civilization had existed on Earth millions of years ago, would we be able to detect it today? The name comes from Doctor Who, the British science fiction series, where reptilian beings called Silurians supposedly evolved intelligence on Earth long before humans appeared. But the scientific version of this idea is far more rigorous and thought-provoking than any television drama. It was developed by astrobiologist Gavin Schmidt and astrophysicist Adam Frank, who wanted to understand what traces our own civilization might leave in the geological record. Their approach was refreshingly honest. Instead of looking for evidence of ancient civilizations, they started by asking what evidence our current civilization would leave behind. This reverse engineering approach helps us understand both the possibilities and the limitations of detecting technological societies in deep time. Consider what future geologists might find if they studied Earth 50 million years from now. Our cities would be long gone. Our roads and buildings would have crumbled and been buried under layers of sediment. Most of our metal tools would have rusted away completely. Even our bones would likely have dissolved in soil and groundwater, leaving behind only the faintest chemical traces. But some things would survive much longer. The concrete in our foundations contains distinctive chemical signatures that could persist for millions of years. The steel reinforcement in that concrete would leave iron deposits in specific patterns. Most remarkably, the enormous quantities of plastic we have produced will leave clear markers in future rock layers. Plastic is one of the most durable materials humans have ever created. Every piece of plastic ever made still exists somewhere on Earth unless it has been deliberately destroyed by burning. Most plastic breaks down into smaller and smaller pieces, but never truly biodegrades. Future geologists would find layers of rock filled with tiny plastic particles, creating what some scientists call the plastic glomerate layer. Our nuclear technology would also leave lasting signatures. The isotopes produced in nuclear reactors and nuclear weapons testing have specific ratios that do not occur naturally. These artificial isotopes would remain detectable in rock layers for millions of years, providing clear evidence of technological activity. Perhaps most significantly, our industrial civilization has dramatically altered the chemistry of Earth's atmosphere and oceans. We have burned enormous quantities of fossil fuels, releasing carbon that was locked away underground for millions of years. This carbon has distinctive isotope ratios that mark it as fossil rather than modern biological carbon. The excess carbon dioxide in our atmosphere is also making the oceans more acidic. This chemical change affects the shells and skeletons of marine organisms in ways that would be preserved in limestone and other sedimentary rocks. Future scientists would see clear evidence of rapid ocean acidification during our time period. Our agriculture has also left chemical fingerprints. We have mined phosphorus and potassium for fertilizers, spreading these nutrients far from their natural sources. We have used nitrogen fixing processes to create artificial fertilizers, changing the nitrogen chemistry of soils around the world. These changes would be detectable in future sedimentary layers. But here is the crucial insight from the Silurian hypothesis. All of these signatures would appear as extremely thin layers in the geological record. Our entire industrial civilization spans only a few hundred years, which corresponds to perhaps a few centimeters of sediment in most environments. Finding and recognizing such thin layers would require both luck and very careful analysis. Moreover, many of the materials we think of as permanent would actually disappear quite quickly on geological timescales. Aluminum and steel corrode within centuries. Glass can persist longer but becomes buried and scattered. Even our most durable plastics might break down over millions of years under the right conditions. This analysis led Schmidt and Frank to a sobering conclusion. Detecting an ancient industrial civilization would be extraordinarily difficult, even if one had existed. The signatures would be subtle, localized, and easily missed or misinterpreted. The absence of obvious evidence does not necessarily mean that such civilizations never existed. Their work also highlighted what kinds of signatures would be most likely to survive and be detected. Chemical changes to the atmosphere and oceans would be preserved in rock layers worldwide. Distinctive isotope ratios from nuclear technology would persist for millions of years. Mass extinctions caused by environmental changes could also serve as markers of technological activity. This leads to an intriguing possibility. Scientists have identified several brief periods in Earth's history when carbon dioxide levels rose rapidly, temperatures increased dramatically, and mass extinctions occurred. The most notable is the Paleocene-Eocene thermal maximum, about 56 million years ago, when global temperatures rose by 5 to 8 degrees Celsius in just a few thousand years. Could events like these have been caused by ancient industrial civilizations rather than natural processes? Most scientists believe these warming events resulted from massive volcanic eruptions or other geological processes, but the Silurian hypothesis reminds us that we should at least consider the possibility of other explanations. The challenge is that the signatures of industrial activity and natural catastrophes can look quite similar in the geological record. Rapid carbon dioxide release, temperature changes, and mass extinctions can result from either technological activity or volcanic eruptions. Distinguishing between these causes requires very careful analysis of multiple lines of evidence. Some researchers have begun looking specifically for the kinds of signatures that the Silurian hypothesis predicts. They search for unusual concentrations of rare metals that might indicate mining and refining activities. They look for isotope ratios that could suggest artificial nuclear processes. They examine patterns of species extinction that might reflect technological rather than natural causes. So far, these searches have not found convincing evidence of ancient industrial civilizations, but they have revealed just how difficult such evidence would be to detect and interpret. The researchers involved emphasize that the absence of clear signatures does not prove that ancient civilizations never existed, only that we have not yet found evidence for them. The Silurian hypothesis has implications far beyond our own planet. As we search for signs of life and intelligence elsewhere in the universe, we need to understand what kinds of signatures technological civilizations actually leave behind. If such signatures are as subtle and short lived as this research suggests, we may need to develop new methods and look for different kinds of evidence. This work also changes how we think about the longevity of civilizations. We often assume that successful technological societies would grow larger and more permanent over time. But the Silurian hypothesis suggests that even highly advanced civilizations might have relatively brief geological lifespans, appearing and disappearing within thin layers of the rock record. Perhaps most importantly, this research provides a new perspective on our own civilization and its relationship to Earth's environment. The chemical signatures we are leaving behind will persist long after our cities have crumbled. Future beings studying Earth's history will see clear evidence of rapid environmental change during our time, even if they find no trace of our buildings or technology. This perspective is both humbling and sobering. It reminds us that our current civilization is just one brief chapter in Earth's long story, but it also suggests that our environmental impacts may be our most lasting legacy, preserved in rock layers that will exist long after every human artifact has disappeared. The Silurian hypothesis also encourages us to think more carefully about what we mean by detectability. Just because we cannot easily find evidence of something does not mean it never existed. The geological record is incomplete and biased towards certain types of preservation. Many significant events and processes leave only subtle traces that require sophisticated analysis to detect and interpret. As we continue our exploration of deep time and the possibility of ancient civilizations, the Silurian hypothesis provides both a methodology and a reality check. It shows us how to think scientifically about traces of intelligence in the geological record, while also demonstrating how challenging such detective work really is. Tonight, as you settle into rest, consider the traces our own civilization is leaving behind. Picture future scientists carefully analyzing rock layers, searching for the chemical signatures of our industrial age. Imagine them puzzling over the meaning of plastic particles and artificial isotopes, trying to reconstruct the story of a technological civilization they never directly observed. Think about the humility this perspective brings to our search for ancient intelligence. We are looking for evidence that may be almost impossibly subtle, hidden within the vast archive of Earth's geological history. Yet the very difficulty of this search makes it all the more important to conduct it carefully and rigorously. Rest knowing that whether or not we ever find traces of ancient civilizations, the search itself teaches us valuable lessons about our own place in the story of Earth. We are part of a long chain of life, an intelligence that stretches back through deep time and forward into an uncertain future. Our role is to be good custodians of this heritage while remaining open to the possibility that we are not the first to bear the responsibility of consciousness in the cosmos. In our next gentle exploration, we will journey through Earth's long history of climate change and consider how these great cycles of warming and cooling might have created windows of opportunity for complex life and civilization to flourish, only to close again as conditions changed. Our planet's climate has never been stable. Instead, it has shifted between warm and cool periods in great cycles that span millions of years. These climate changes have created and destroyed opportunities for life to flourish, and they might help us understand when and where ancient civilizations could have existed. Earth's climate system breathes like a living thing, expanding into warm periods and contracting into cool ones. This breathing happens on multiple timescales, from the familiar cycles of seasons to vast geological rhythms that play out over millions of years. Understanding these patterns helps us see our current climate in perspective and imagine how past climates might have supported different forms of life. The Boli's ages we explored earlier are just the most recent examples of Earth's climate cycles. For the past 2.5 million years, our planet has alternated between glacial periods when ice sheets covered much of the northern continents and interglacial periods like the one we live in now. These cycles are driven by subtle changes in Earth's orbit around the Sun, changes so small that they seem insignificant until they accumulate over thousands of years. The Serbian mathematician Milutin Milankovic first described these orbital cycles in the early 20th century. He showed how variations in the shape of Earth's orbit, the tilt of its axis, and the wobble of its rotation combine to create predictable patterns of climate change. When these cycles align in certain ways, they can trigger ice ages or bring them to an end. But the Ice Age cycles represent only a small portion of Earth's climate history. For most of the past 500 million years, our planet was much warmer than it is today. There were no permanent ice caps. At the poles, sea levels were higher, sometimes by hundreds of meters. Forests grew near the North and South poles. These warm periods, which scientists call greenhouse climates, created very different opportunities for life than the cooler climates we are familiar with. During the Eocene period, about 50 million years ago, Earth experienced one of its warmest climates in recent geological history. Global temperatures were perhaps 8 to 10 degrees Celsius warmer than today. There was no ice anywhere on the planet. Palm trees grew in Alaska, and crocodiles lived in the Arctic Ocean. The configuration of continents was different too, which helped create more even temperatures around the globe. This warm Eocene world would have been nearly unrecognizable to us. The geography was different because the continents were still moving toward their current positions. The Atlantic Ocean was narrower. India had not yet collided with Asia to form the Himalayas. The climate was so warm and humid that vast rainforests covered much of the planet, even in regions that are now deserts or grasslands. What makes the Eocene particularly interesting for our exploration is that it was also a time of rapid evolutionary innovation. Many modern mammal groups first appeared during this period. The warm climate and abundant vegetation supported diverse ecosystems. Intelligence in mammals was beginning to develop in new directions. If we are looking for windows of time when complex societies might have emerged, warm, stable periods like the Eocene seem particularly promising. Even more dramatic was the Cretaceous period, from about 145 to 66 million years ago. This was the height of the age of dinosaurs, but it was also a time of extraordinary warmth. There were no ice caps at all. Sea levels were so high that shallow seas covered much of what are now the central parts of continents. The climate was warm and humid everywhere, creating lush tropical conditions even in polar regions. The Cretaceous greenhouse climate supported some of the largest and most diverse ecosystems in Earth's history. Dinosaurs reached their greatest size and complexity during this time. Flowering plants evolved and spread rapidly, creating new types of habitats and food webs. The warm climate meant that seasonal differences were minimal, creating stable conditions that could support complex long-term social structures. But greenhouse periods do not last forever. They are interrupted by cooling events that can happen quite rapidly in geological terms. The transition from the warm Eocene to cooler conditions happened over just a few million years. As temperatures dropped, ice began to form at the poles, sea levels fell. Ecosystems that had flourished in the warmth were forced to adapt to new conditions or disappear entirely. These transitions between warm and cool climates can be particularly challenging for complex life forms. Species that are highly specialized for warm conditions may not be able to adapt quickly enough when the climate cools. Social structures that depend on abundant resources may collapse when those resources become scarce. Any hypothetical ancient civilizations would have been especially vulnerable during these transition periods. The causes of these long-term climate cycles are complex and not fully understood. Changes in ocean circulation patterns play an important role. When continents move to new positions, they can block or redirect ocean currents, dramatically altering heat transport around the globe. The formation of mountain ranges can affect atmospheric circulation and precipitation patterns. Volcanic activity can release greenhouse gases or inject particles into the atmosphere that reflect sunlight back to space. Sometimes climate changes happen much more rapidly than the gradual orbital cycles would predict. The Paleocene-Eocene thermal maximum, which we mentioned when discussing the Silurian Hypothesis, was one such event. About 56 million years ago, global temperatures rose by 5 to 8 degrees Celsius in just a few thousand years. This rapid warming was accompanied by ocean acidification and mass extinctions in marine ecosystems. Scientists believe this rapid warming was caused by the sudden release of enormous amounts of carbon dioxide into the atmosphere. The source might have been massive volcanic eruptions, the destabilization of methane deposits on the ocean floor, or some combination of factors. Whatever the cause, the event shows how quickly Earth's climate can shift from one state to another. These rapid climate changes create both opportunities and challenges for life. On one hand, they can disrupt established ecosystems and cause extinctions. On the other hand, they can also create new niches and drive evolutionary innovation. Species that can adapt quickly to changing conditions may find themselves with access to resources that were previously unavailable. For potential ancient civilizations, rapid climate changes could have been catastrophic or liberating, depending on their circumstances. A civilization adapted to cool conditions might flourish if global warming suddenly made new territories habitable. Conversely, a civilization dependent on stable climate patterns might collapse if those patterns shifted too quickly for social and technological adaptation. The relationship between climate and habitability is not straightforward. While we might assume that warm periods are automatically better for complex life, the reality is more nuanced. Extremely hot conditions can be just as challenging as extremely cold ones. Very high temperatures can disrupt the biochemical processes that life depends on. High humidity can favor the spread of diseases. Rapid sea level changes can flood established territories or strand coastal communities far from the water. Moderate climates with stable seasonal patterns may actually be more favorable for the development of complex societies than either extreme warmth or extreme cold. Such conditions provide predictable resources without the stress of constant environmental change. They allow long-term planning and the accumulation of knowledge across generations. Unfortunately, these moderate, stable conditions have been relatively rare in Earth's history. The Sahara Desert provides a fascinating example of how dramatically regional climates can change. Today, it is one of the most arid places on Earth, but for much of the past 10,000 years, it was a green landscape of grasslands and lakes. Rock art from this period shows people and animals thriving in what is now barren desert. The transformation from green Sahara to desert happened gradually as changes in Earth's orbit shifted rainfall patterns. This example reminds us that even during relatively stable global climate periods, regional climates can undergo dramatic transformations. A civilization that developed in a favorable regional climate might have thrived for thousands of years before environmental changes made their territory uninhabitable. Their ruins might now lie buried beneath desert sand or submerged beneath risen seas. Antarctica provides another example of dramatic climate transformation. Today it is covered by ice sheets up to 4 kilometers thick, but for much of Earth's history it was warm and green. Fossil discoveries show that forests once grew near the South Pole. If ancient civilizations had developed in what is now Antarctica, their remains would be buried beneath enormous masses of ice, virtually impossible to detect with current technology. As we consider the possibility of ancient civilizations, climate cycles help us understand when and where such civilizations might have existed. Warm, stable periods, lasting millions of years, provided ample time for intelligence to evolve and complex societies to develop. The transitions between climate states created both challenges that might have destroyed civilizations and opportunities that might have spurred their development. Climate cycles also help explain why evidence of ancient civilizations might be so difficult to find. The same processes that drive long-term climate change also reshape Earth's surface. Rising and falling sea levels bury some regions under sediment while exposing others to erosion. Changing vegetation patterns alter soil chemistry and preservation conditions. The advance and retreat of ice sheets scrape away surface features and redistribute sediments over vast distances. Perhaps most importantly, climate cycles remind us that Earth's surface has never been static. The world has been many different worlds over geological time. Each configuration of climate, geography, and life has created its own possibilities and constraints. What seems impossible in our current world might have been commonplace in past worlds with very different environmental conditions. Tonight, as you settle toward rest, imagine Earth breathing through its great climate cycles. Picture vast ice sheets advancing and retreating like slow tides. Envision tropical forests spreading toward the poles during warm periods and retreating toward the equator during cool ones. Think about the countless ecosystems that have risen and fallen with these climate rhythms. Consider how these cycles might have provided opportunities for intelligence to emerge in forms we have never imagined. Warm, stable periods lasting tens of millions of years could have supported experiments in consciousness and civilization that we can barely conceive. The transitions between these periods might have challenged and transformed such civilizations in ways that left no obvious traces for us to discover. Rest knowing that we live within these same great cycles that have shaped life for hundreds of millions of years. Our current interglacial period is just one brief moment in Earth's ongoing climate story. Future beings looking back at our time will see us as products of specific climate conditions that enabled our particular form of civilization to emerge and flourish. In our next exploration, we will examine the sophisticated knowledge that ancient human civilizations developed about astronomy, mathematics, and engineering. We will discover how much past peoples knew about their world and consider whether this knowledge might represent something even older and more mysterious than we usually assume. Throughout history, people have possessed knowledge that seems surprisingly advanced for their time and circumstances. Tonight, we explore these puzzles of ancient wisdom and consider what they might reveal about the depth of human understanding across the ages. In the jungles of Central America, Mayan astronomers developed calendars more accurate than those used in medieval Europe. Without telescopes or modern instruments, they tracked the movements of Venus with precision that amazes contemporary scientists. Their calculations predicted eclipses centuries in advance. They understood that Venus takes exactly 584 days to complete its cycle as seen from Earth, a figure that matches modern measurements almost perfectly. The Maya were not unique in their astronomical sophistication. Ancient Babylonians created mathematical models of planetary motion that remained unsurpassed for over 1,000 years. They divided the circle into 360 degrees and developed sophisticated methods for predicting when planets would appear in specific positions. Their mathematical tablets reveal an understanding of astronomy that we might expect only from cultures with advanced scientific institutions. Along the Nile River, Egyptian architects and engineers accomplished feats that continue to challenge our understanding. The Great Pyramid of Giza was built with such precision that its base forms an almost perfect square, with sides that differ in length by less than 2 centimeters. The pyramid's orientation aligns with cardinal directions to within 3/60ths of a degree. These achievements required not only skilled craftsmanship, but also sophisticated knowledge of mathematics and surveying. The ancient Egyptians also demonstrated remarkable understanding of human anatomy through their mummification practices. Medical papyri describe surgical procedures and treatments that show detailed knowledge of the circulatory system, brain function, and disease processes. Some of their medical insights were not rediscovered by European medicine until the Renaissance, over 1,000 years later. Across the Mediterranean, Greek thinkers made discoveries that laid the foundation for modern science. Eratosthenes calculated the circumference of Earth around 2,200 years ago using only shadows and simple geometry. His result came within a few percent of the true value. Aristarchus proposed that Earth orbited the Sun, anticipating Copernicus by over 17 centuries. Hipparchus developed trigonometry and discovered the precession of Earth's axis. Perhaps most intriguing is the Antikythera mechanism, sometimes called the world's first computer. This bronze device, recovered from a shipwreck off the Greek coast, contains over 30 precisely cut gear wheels that work together to predict the positions of celestial bodies. Dating from around 2,000 years ago, it demonstrates a level of mechanical sophistication that was not seen again in Europe until the development of clockwork in the medieval period. The device could predict eclipses, track the 4-year cycle of Olympic Games, and show the phases of the moon with remarkable accuracy. Recent analysis reveals that it incorporated the irregular motion of the moon as understood by the astronomer Hipparchus. Creating such a mechanism required not only advanced mathematical knowledge, but also highly skilled metalworking and precision engineering techniques. In Baghdad, during what Europeans call the Dark Ages, scholars preserved and expanded upon Greek learning while making original discoveries. The Persian mathematician Al-Khwarizmi developed algebra and introduced the decimal number system to the Islamic world. Ibn al-Haytham pioneered the scientific method and made fundamental discoveries in optics that influenced European science centuries later. Some artifacts from this period remain mysterious. The Baghdad battery, a ceramic jar containing a copper cylinder and iron rod, could theoretically produce electrical current when filled with an acidic solution. While its actual purpose remains debated, its construction suggests knowledge of electrochemical principles that were not formally understood in Europe until the 18th century. In ancient China, innovations appeared that would not reach Europe for centuries. Chinese engineers developed seismographs, magnetic compasses, and mechanical clocks with escapement mechanisms. They discovered gunpowder, invented printing with movable type, and created paper money. Chinese astronomers maintain detailed records of celestial events that modern scientists still consult when studying historical supernovas and comets. The precision of Chinese astronomical observations is particularly remarkable. Records from over 2,000 years ago describe the appearance of new stars that we now know were exploding supernovas. The positions and dates recorded by Chinese astronomers allow modern astrophysicists to locate and study the remnants of these stellar explosions. Such accuracy required systematic observation and record keeping over many generations. Across the Pacific, Polynesian navigators accomplished feats of exploration that rival any in human history. Without written maps or modern instruments, they sailed across thousands of kilometers of open ocean to discover and settle remote islands. Their navigation methods, based on reading ocean swells, wind patterns, and star positions, allowed them to find tiny specks of land in the vast Pacific with remarkable consistency. These navigational skills were passed down through generations of master navigators who memorized complex systems of knowledge about ocean currents, seasonal weather patterns, and the behavior of marine life. Star maps made of sticks and shells help teach the positions of navigation stars and the directions to distant islands. The precision of this knowledge system enabled migrations across oceanic distances that Europeans did not attempt until they had developed sophisticated sailing ships and navigation instruments. In the Americas, indigenous peoples developed mathematical and astronomical knowledge independently of Old World civilizations. The Inca managed a vast empire without written language, using instead a system of knotted cords called quipu that could record complex numerical and possibly narrative information. Their architecture demonstrates sophisticated understanding of earthquake-resistant construction and precision stone-cutting techniques. The Nazca people of Peru created enormous ground drawings that are fully visible only from the air. These geoglyphs demonstrate not only artistic vision, but also sophisticated surveying techniques needed to maintain proper proportions across distances of several kilometers. How they planned and executed these massive projects without aerial perspective remains an intriguing puzzle. What makes all these achievements particularly fascinating is that they often appear to emerge suddenly in the historical record without obvious precursors. The Antikythera mechanism represents a level of mechanical complexity that seems to have no developmental history in Greek technology. Mayan astronomy reached remarkable sophistication relatively quickly after the civilization's emergence in the historical record. This pattern raises interesting questions about how knowledge develops and spreads. Perhaps these civilizations, built upon much older traditions of learning that were transmitted orally for generations before being recorded in permanent form. Perhaps sophisticated knowledge was more widespread in the ancient world than surviving records suggest, with many achievements lost when libraries burned or manuscripts decayed. The phenomenon of lost knowledge is well documented in human history. The Romans developed concrete formulations that remained superior to later European concrete until modern times. Medieval European builders lost the techniques for creating the large window spans seen in Roman architecture. The formula for Greek fire, the incendiary weapon of the Byzantine Empire, was so closely guarded that it eventually disappeared entirely. If knowledge can be lost within relatively short periods of historical time, how much more might have been lost over the vast spans of prehistory? Advanced understanding of astronomy, mathematics, engineering, and medicine might have developed and disappeared multiple times throughout human history, leaving behind only the faintest traces in the achievements that have survived. The Baghdad Battery reminds us that our ancestors might have discovered principles that we consider modern innovations. If ancient peoples could stumble upon electrochemical effects, what other scientific principles might they have uncovered through careful observation and experimentation? The boundary between ancient wisdom and modern science may not be as clear as we sometimes assume. This possibility becomes even more intriguing when we consider that human intelligence and curiosity have remained essentially unchanged throughout recorded history. Ancient peoples had the same cognitive capabilities that modern scientists possess. Given enough time and motivation, there is no fundamental reason why they could not have made sophisticated discoveries about the natural world. The preservation of knowledge is as much a challenge as its discovery. Without printing presses or digital storage, ancient peoples had to rely on human memory, fragile manuscripts, and careful training of students to preserve their insights. A single war, plague, or natural disaster could wipe out generations of accumulated learning. The wonder is not that so much knowledge was lost, but that so much has survived. Yet this fragility of knowledge preservation also suggests intriguing possibilities for our larger question about ancient civilizations. If human societies could develop sophisticated understanding of astronomy, mathematics, and engineering multiple times throughout history, perhaps non-human intelligences could have done so as well over the much longer spans of geological time. The difference between possessing advanced knowledge and creating an advanced civilization is subtle but important. The Maya had sophisticated astronomy but did not develop industrial technology. Ancient Greeks understood mechanical principles but did not trigger an industrial revolution. Knowledge and technology can develop along many different paths, not all of which lead to the kinds of material traces that would be easily preserved in the geological record. This suggests that ancient intelligences, whether human or otherwise, might have achieved remarkable sophistication in areas that would leave few lasting traces. Astronomical knowledge, mathematical insights, understanding of natural cycles, and complex social organization might have reached high levels without producing the kinds of artifacts that modern archaeology typically looks for. Tonight, as you settle into rest, consider the countless generations of curious minds that have observed the stars, pondered natural phenomena, and sought to understand their place in the cosmos. Picture ancient astronomers tracking planetary motions night after night, gradually building mathematical models of celestial mechanics that rival our modern understanding. Think about the master navigators who could read the ocean like a familiar landscape, using knowledge passed down through generations to find their way across vast expanses of water. Imagine the architects and engineers who moved massive stones and built monuments that still stand thousands of years later, their techniques sometimes surpassing our modern capabilities. Rest knowing that human curiosity and ingenuity extend far back into our species' past. The questions we explore about ancient knowledge and lost civilizations connect us to this deep tradition of wonder and discovery. Whether or not other intelligences preceded us on Earth, the human story itself reveals the remarkable potential of conscious minds to uncover the secrets of nature and cosmos. In our next exploration, we will step even further back in time to consider the earlier experiments in intelligence and complexity that life has conducted on our planet. We will discover that the path to consciousness has been explored many times by many different kinds of creatures, each finding their own unique solutions to the challenges of existence. Life's story begins in the sea. Long before humans or even dinosaurs appeared, life experimented with endless forms beneath ancient oceans. Tonight, we will visit these early experiments in intelligence and complexity, imagining the myriad ways life has explored consciousness on our planet. Over 500 million years ago, during the Cambrian explosion, the oceans teemed with new creatures. In just a few tens of millions of years, life went from simple blobs to complex animals with eyes, limbs, and hard shells. Among these pioneers were trilobites, creatures with segmented bodies and compound eyes that could detect motion and light with remarkable sensitivity. Trilobites lived in large communities on the seafloor. They molted their exoskeletons as they grew, leaving fossilized remnants that tell us about their behavior and development. Some trilobite species formed huge swarms, migrating in massive numbers. Their complex eyes and social behaviors suggest a level of awareness suited to avoiding predators and finding food. Meanwhile, other Cambrian creatures explored different forms of complexity. Anomalocaris, a shrimp-like hunter over a meter long, chased small prey with agile movements and keen vision, while Hallucigenia, with its spiky back and tentacle-like limbs, navigated the dimly lit seabed in search of nourishment. Millions of years later, the age of dinosaurs ruled the land, but intelligence was not limited to reptiles. Troodon, a small dinosaur with large eyes and a brain-to-body ratio similar to modern birds, may have been one of the most intelligent non-avian dinosaurs. It hunted in packs, used tools such as sticks to probe for food, and may even have had social structures to coordinate group hunting. In the seas, cephalopods, squid, octopus, and their kin began exploring intelligence along a separate evolutionary path. Their soft bodies and complex nervous systems allowed rapid learning and camouflage. Today's octopuses can solve puzzles, open jars, and use coconut shells as portable shelters. Their ancestors, appearing over 300 million years ago, started evolving these traits in ancient oceans, experimenting with nervous systems very different from those of vertebrates. On land, the rise of mammals after the end of the dinosaurs marked another chapter in life's experiments. Early mammal ancestors were small and nocturnal, navigating dark forests with keen senses of hearing and smell. Over tens of millions of years, some lineages evolved larger brains and more complex social structures. Corvids, crows, ravens, and jays offer another example of convergent intelligence. These birds evolved large brains and problem solving abilities independently of mammals and reptiles. They fashion tools from twigs, remember hundreds of hiding places for food, and even plan for the future. Their evolution shows that intelligence can arise in many forms when ecological pressures favor adaptability. Social insects, like ants and bees, demonstrate that individual intelligence is not the only path. In ant colonies, thousands of simple individuals collaborate to solve problems that far exceed the capabilities of any single ant. They build complex nests with ventilation systems, farm fungus as food, and wage wars with neighboring colonies, all through decentralized decision making and chemical communication. Each of these lineages represents an experiment in complexity and intelligence. They show that life on Earth has repeatedly explored new ways to gather information, solve problems, and adapt to changing environments. These experiments have taken millions of years, producing a kaleidoscope of solutions to the challenges of survival. What does this mean for our search for ancient civilizations? It suggests that intelligence and complex social behavior are not unique to humans and may have evolved many times in Earth's history. If intelligence can arise in trilobites, dinosaurs, mammals, cephalopods, birds, and insects, it is possible it has appeared and vanished in other lineages we have yet to imagine. Some of these experiments may have taken paths that left little trace in the fossil record. Soft-bodied creatures rarely fossilize. Complex behaviors and social structures do not leave direct physical evidence. If an intelligent species arose in the ocean depths or in underground habitats, their traces might be hidden in ways we do not yet know how to detect. Tonight, as you drift into the realm of dreams, imagine life's earliest explorers on Earth's great stage. See the trilobites swarming across the seafloor in prehistoric seas. Picture the swift troodons chasing prey under ancient trees. Feel the shifting sands of Octopus Garden, where soft-bodied cephalopods played in hidden caves. Envision ant colonies building their intricate cities in prehistoric forests. Consider how these varied experiments in intelligence hint at the deep potential of life to find creative solutions to survival. Our human story is only one of many possibilities that life has explored. Each experiment has enriched the web of life with new forms and new capacities. Rest knowing that the tapestry of life on Earth is woven from countless threads of innovation and adaptation. We are part of this grand experiment, carrying forward the legacy of all the creatures that came before us and all that will follow. As you sleep, let your mind wander through the ancient seas and forests, where intelligence bloomed in endless forms, each a reminder of the boundless creativity of life itself. In our exploration so far, we have seen intelligence arise in many forms and explored Earth's record of deep time. Now we ask a simple but profound question. What exactly do we mean by civilization? How would we recognize it in the distant past? And might non-human societies have achieved it long before humans? When archaeologists study human history, they look for certain markers: cities with streets and walls, writing systems, monuments and tools, showing specialization of labor. These features indicate organized societies capable of planning, record keeping, and building durable structures. Cities like Uruk in Mesopotamia emerged around 6,000 years ago, with tens of thousands of residents, centralized administration, and complex trade networks. Writing is another hallmark. Early Sumerian cuneiform records, grain rations, temple accounts, and laws. Writing allows societies to transmit detailed information across generations, preserving contracts, histories, and technical knowledge. Without writing, complex bureaucracies and legal systems become difficult to maintain at large scales. Specialization of labor: farmers, artisans, priests, rulers, reflects social stratification and the ability to sustain non-food producing classes. Artisans create goods of luxury and utility, while priests and rulers guide religious and political life. This division of labor depends on stable food surpluses produced by agriculture and animal husbandry. But civilization may be defined more broadly. Anthropologists consider culture, language, art, and social complexity as equally important. Civilizations develop shared beliefs, rituals, and artistic expressions that bind communities together. The intricate woven patterns of Andean textiles or the elaborate dance rituals of Pacific Islanders show cultural sophistication even without cities or writing. Technology also plays a key role. Tool use is not unique to humans. Many animals use sticks or stones, but true technological civilization involves systematic innovation and cumulative improvements. Humans invented metallurgy, wheel and axle, and water control systems like irrigation canals and aqueducts. These technologies required planning, resource management, and coordination on scales beyond small groups. Social organization extends beyond human examples. Ant colonies, for instance, build complex nests with ventilation and temperature control. They farm fungus and herd aphids, demonstrating agriculture-like behaviors. Beehives have distinct castes and communicate through dances. These insect societies meet many anthropological definitions of civilization: shared culture, division of labor, environmental modification, and record keeping through chemical signals. Whales and dolphins exhibit cultural behaviors too. Pods have unique vocalizations, dialects that are passed from generation to generation. They use cooperative hunting techniques, beaching themselves to catch prey, and teach these methods to young. Some orca populations specialize in particular prey, showing cultural transmission of hunting strategies over decades. Octopuses, though solitary, use tools like coconut shells and rocks to build shelters. They can solve puzzles, escape enclosures, and demonstrate remarkable problem-solving skills. Their short lifespans limit cultural transmission across generations, but their individual intelligence hints at alternative forms of societal complexity. If we broaden our definition, civilization might encompass any community with knowledge transmission, environmental modification, and social cooperation beyond basic survival. Under this view, diverse life forms could qualify. The key challenge is recognizing these markers in the fossil record or geological layers. Chemical traces of agriculture, altered soil nutrients, might hint at farming by non-human species. Structures built of mineralized secretions, like coral reefs, already shape environments on massive scales. Could these represent civilization-like behaviors? Coral cities house countless species and grow complex three-dimensional structures over millennia. Recognizing civilization in deep time requires us to look for patterns of environmental change that suggest intentional modification. Distinctive chemical signatures in soils, sudden shifts in local biodiversity, and unusual sediment patterns could point to large-scale habitat engineering by intelligent organisms. The bias of archaeology towards stone, metal, and written records may blind us to civilizations that relied on organic or ephemeral materials. Wooden structures, woven fabrics, and oral traditions leave little trace after centuries, let alone millions of years. Yet these materials may have been primary media for many past societies, human and otherwise. As you rest tonight, imagine a world where intelligence took forms we cannot easily conceive. Picture ant farmers cultivating fungus in underground chambers. Visualize marine architects building reef cities with fine control of calcium carbonate deposition. Envision aerial civilizations of winged creatures weaving nests of silk and pollen high in the forest canopy. Consider the possibility that civilization does not require human-like cities or technology. It may manifest as persistent environmental shaping, complex communication systems, and cultural transmission across generations. These forms of civilization could leave only subtle marks on rocks and sediments, marks that scientists are only beginning to learn to recognize. Ultimately, the question of what defines a civilization reminds us to remain open-minded. Civilization is not a single path toward skyscrapers and satellites. It is a tapestry of many paths toward organized, knowledge-based, and cooperative life. On Earth's vast canvas, we are but one thread in a rich array of possibilities. Rest knowing that your capacity for curiosity and empathy links you to all forms of life that have ever wrestled with the meaning of community and knowledge. Whether or not we find evidence of ancient non-human civilizations, our search reflects the deepest human longing to understand our place in the grand story of life on Earth. Imagine stepping far into the future, tens of millions of years from now, when humans no longer walk the Earth and our cities have returned to dust and soil. In that distant era, researchers will piece together our story from the subtle clues we leave behind. Tonight, we will become those future archaeologists, exploring what remnants of our civilization might survive and how they will be interpreted. First, they will search for the most obvious markers, the deep layers of plastic pollution that blanket coastlines and ocean sediments. Tiny fragments of polyethylene and polypropylene will mingle with sand grains, forming distinct strata. Future scientists will name this the plastic glomerate layer, a testament to our disposable culture and mass production of synthetic materials. They will find traces of concrete foundations, now fractured and buried, but still discernible by their unusual mineral composition. Reinforcing steel bars will leave iron-rich streaks through sediment layers. The characteristic chemical signatures of cement, calcium silicates, and aluminates will persist long after the stones crumble, marking the footprints of our cities and roads. Next, they will trace the isotopic signals of our industrial era. Carbon isotope ratios in sediment cores will shift abruptly as ancient forests were burned and fossil fuels consumed. Elevated levels of carbon 14 from nuclear testing will pepper the timeline, marking mid 20th century experiments and weapons tests. These nuclear markers will remain detectable for millions of years, a clear sign of a civilization capable of splitting atoms. Deep ocean sediments will preserve evidence of ocean acidification. Microscopic shells of plankton will show thinning walls and changes in species diversity as rising carbon dioxide altered seawater chemistry. These subtle but global markers will reveal a period when life struggled to adapt to rapid environmental change caused by an intelligent species. They will uncover metal enrichment zones where mining and refining once took place, trace concentrations of copper, aluminum, and rare earth elements will cluster around ancient deposits. Unusual ratios of lead and zinc will suggest smelting activities, while elevated platinum group metals may hint at industrial catalysts and electronics production. These chemical hotspots will map out ancient industrial districts. Certain locations may preserve more dramatic remains. In desert regions, arid climates, slow decay, buried under sand dunes, a portion of a glass skyscraper facade might survive as fused silica panels amid dune sands. In regions of permafrost, wooden beams from old buildings may be frozen in time, their cellulose structure intact for millennia, awaiting discovery when climate fluctuations expose them once more. Future archaeologists will learn to read the ley lines of underground infrastructure. Subterranean subway tunnels and utility conduits will collapse but may leave voids and patterns detectable by ground, penetrating sensors. Networks of pipes, once water mains, sewers, and fiber optic cables, will create linear anomalies echoing the layout of vanished cities. They will find cultural artifacts too. Disk drives and memory chips sealed in lead vaults may survive as corroded, but legible objects, ceramic art pieces and porcelain dishes, if buried deep enough, could endure virtually unchanged, offering glimpses of daily life and aesthetic tastes. Irrigation canals and terraced fields will be visible in regions where agricultural practices were extensive. Layers of dark, nutrient-rich soil will mark ancient farmlands, now long abandoned. Pollen records in sediment cores will show sudden expansions of domesticated plant species, wheat, rice, maize, indicating large-scale cultivation by intelligent hands. In polar regions, ice cores will encapsulate tiny bubbles of our polluted air, sulfur and nitrogen compounds from coal burning, particulate matter from vehicle exhaust, and even traces of chlorofluorocarbons will be trapped in crystalline layers. These frozen archives will offer precise year-by-year records of human influence on the atmosphere. Piecing together these clues, future researchers will reconstruct a civilization that grew rapidly, reshaped environments on a global scale, and then declined as resources dwindled and climates shifted. They may debate whether our rise constituted a true industrial age or a brief geological anomaly lasting mere grains of sediment time. The archaeological picture may be incomplete. Entire chapters of our history could be missing, records lost in the tropics, where decay is swift or erased by tectonic activity. Mountain building and erosion will have recycled much of the crust where our early civilizations once thrived. Yet even these gaps will tell a story. Regions once home to great early empires may show no sign of human occupation, leaving hypothetical investigations into vanished societies based on statistical models of where human suitable climates existed in deep time. In their journals, future archaeologists may write with humility, "We see hints of a rapid technological explosion, evidence of global coordination, and signs of environmental imprint." Yet the full picture escapes us, reminding us of the fragility of civilizations against the slow but inexorable forces of geology. As you drift into sleep, picture these future researchers kneeling beside a sediment core, gently unwrapping layers like pages of a book. See them marvel at the tiny plastic fragments, the iron streaks, the pollen grains. Hear them whisper questions about who we were and what we valued. Rest knowing that even if our cities vanish, our legacy will endure in the chemistry of rocks, the patterns of buried landscapes, and the frozen archives of ice. Future generations, human or otherwise, may one day piece together our story from these faint echoes, marveling at the brief flicker of intelligence that once reshaped a planet before yielding again to the rhythms of deep time. Gentle threads of thought have guided us through deep time's vast landscapes. We began by quietly stepping into Earth's 4.5 billion year story and defining civilization beyond our usual limits. We read the library of stone and geological layers, dove beneath ancient seas to find sunken cities, and marveled at towering monoliths built by human hands. We witnessed life's resilience through extinction and renewal, listened to cultural echoes and myths, and embraced scientific rigor in the Silurian Hypothesis. We explored climate's grand rhythms, pondered ancient knowledge, and traced intelligence's many experiments across life's tapestry. Now we gather these threads into a final, peaceful reflection. Civilization, in its broadest sense, is a dance between intelligence and environment, memory and material trace, creation and erosion. It is not a fixed monument, but a living process of adaptation, innovation, and storytelling. Over billions of years, life on Earth has repeatedly shaped its world and been reshaped in turn by the slow, patient forces of plate tectonics, climate change, and geological recycling. Our own civilization shines as one brief spark in deep time. Its traces, plastic layers, isotopic markers, buried foundations, may endure for millions of years, yet remain subtle in the geological archive. Future explorers will piece together our story from these faint echoes, just as we have pieced together the stories of those who came before. The search for ancient civilizations, whether human or otherwise, invites humility and wonder. It reminds us that absence of evidence is not proof of absence, and that the most profound discoveries may lie hidden beneath layers we have yet to read. As you drift toward restorative rest, carry with you the gentle hum of deep time's rhythms. Imagine life's earliest stirrings in primordial seas, the rise and fall of empires, both stone and organic, and the countless experiments in intelligence that have graced our world. Let the knowledge that we are part of this grand tapestry bring comfort and inspiration. May this journey leave you with serene curiosity and a peaceful heart. Know that every question we ask adds a new thread to life's ongoing story, and perhaps in dreams you will wander through hidden ruins and befriend the echoes of civilizations lost to time, carrying their quiet wisdom into dawn's gentle light.